Interpreting C13 NMR spectra. Have you got it? This short video quiz assesses your ability to determine the number of expected signals in a standard proton-decoupled C13 spectrum and your ability to use that information to aid in the determination of a molecular structure from combined proton and C13 NMR data. This quiz consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video, try at least to solve the problem yourself, and then only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, for each compound below, predict the number of signals in its C13 NMR spectrum. Pause the video while you answer this question. I'll be back in a minute. Okay, we're back. Let's see what we've got here. In this first case, a CH3 next to a CH2 next to a carbonyl group. Don't forget that carbonyl group. Carbon here with no hydrogens. 2 carbons flanking that. 2 carbons next to those. The final carbon in the ring next to the oxygen. A CH and 2 CH3s. 1, 2, 3, 4, 5, 6, 7, 8, 9. The next one, we have a plane of symmetry here. So it's 1, 2, 3. Another plane of symmetry here. We're going right through all these atoms. So 1, 2 flanking, 2 flanking, the far one, the CH, and very similar to that aromatic ring. 1, 2, 3, 4, 5, 6 this time. All right, what about this one? Oh, this one might surprise you. We certainly have all 6 in the ring. They're all different. 7. Now, what about these 2 methyl groups? You want to consider them the same, probably. But if you think about it, this compound has a stereocenter right here. And that means that one of these methyls is in a different relationship to the alkene than the other, and those are different. So it's 6, 7, 8, 9. Down here, plane of symmetry. That's giving us 1, 2, 3, 4, 5. And in this case, plane of symmetry here, but also a plane of symmetry here. So that means we have the methyl, the tertiary carbon on the ring, and one of the ring CH2s, and that's it. What'd you do with this one? It's a cyclohexane. It's got a huge number of planes. It's got a huge number of axes. For example, here's an axis right here that we rotate 180 degrees. We get the top and the bottom flipping to be themselves. So actually, there's just one here. It's a little different on this last one. Some of these planes are gone, but the plane that's still there is this one right here. I don't think we can do any C2 business on this because of that. So it's going to be 1, 2, 3, 4. How'd you do? Okay, this predicting the number of signals is the first thing we do for all C13 spectral analysis, because what we're looking for in C13 is a certain number of peaks. So at 9, 3, 6, 9, 5, 3, 1, 4, that's exactly the sort of information that we need. Number 2, the following reaction was carried out and the major product was isolated and analyzed by proton and C13 NMR spectroscopy. This display format shows the C13 spectrum directly above the proton spectrum. Which compound was the major product, A or B? Give you a few seconds to work on that. Come back, see how fast you can figure this out. Key in on the key information you need and nothing more. Pause the video while you answer this question. Okay, we're back. Well, the interesting thing about this case is that, the proton spectrum is really complicated. It's not like we're going to be able to get much information from that. Now, if you're very clever, you could answer it with just a NMR from the protons, but the C13 is really the easiest one. First thing to realize that this C13 was taken in deuterochloroform. That means there is a carbon in the solvent, and the solvent will appear with the compound. And that is this little thing here, which at 77 is a group of 3 lines, 1, 2, 3. And that is the signal for deuterochloroform. Okay, so the others are significant. And if you look at the spectrum, we have 1, 2, 3, 4, 5, 6, 7 lines. Now, looking at the compounds that we have, what do we expect? Well, in this case on the right, B, we have 1, 2, 3, 4, 5, 6, 7. But look at this one on the left. We have 1, 2, 3, 4, 5. But then these two are equivalent. So there's only 6 lines here. And the fact that we have 7 lines tells us it's product B. This is very common to be able to distinguish compounds by the number of carbon signals. Very quick analysis. You don't have to learn anything about the splitting because there's no splitting in a C13 spectrum. There's nothing about integration in the C13 spectrum. It's just a bunch of lines. So if you can detect those lines, see that they match your number of carbons, you can continue, but if they are not, it can't be that compound. Alrighty, number 3. Here's a challenge. The proton and C13 spectra of dimethoxybenzene got all mixed up. Set them straight, matching them with the appropriate compound. So what we have here are 3 isomers of dimethoxybenzene, 1, 2, 1, 3, 1, 4. We've got 3 proton spectra. We have 3 carbon spectra. See if you can figure this out. Which is the carbon and the proton for the 1, 2, which is the carbon and proton for the 1, 3, and which is the carbon and the proton spectrum for 1, 4. Pause the video while you answer this question. Okay, well, this is a really interesting problem, I think, and a little bit challenging because we have the dissociation of the C13 and the proton, so we're going to have to do those independently. The other thing we have here that you can see is a significant amount of noise in the C13 spectrum, and this is part of the lesson on this. One of the problems in C13 is that because C13 is only 1.1% natural abundance, signals are much weaker, and it takes more scans, and sometimes we don't take as many scans as we wished, and the signals are not much higher than the noise. So again, we're just going to ignore these deuterochloroform signals and look at the others. And the key thing that I wanted to point out here is that we do have signals down here in the 140 to 160 range. This whole region from about 100 to 160 is the aromatic ring region. Every one of them has this spike at around 55 or so, which is our methoxy peak, right? So the CH3, OCH3 in each case, is showing up as a single peak. In each case, we have the symmetry. So in each case, we have a signal peak, and there's not much we can do with that. But now, what we want to do is count the number of C13 signals. In the top case, we have 3. 1, 2, 3. That one far off to the left is the one with the oxygen in each case. That's why it's so far to the left. In the second case, we have 2. And in the third case, we have 1, 2, 3, 4. So what do we got up here? In the first case of 1, 2, we have plane of symmetry here. So there's 1, 2, 3 aromatics. In the 1, 3 case, we have the carbon between the two, our mirror is going that way. We have the one that's across, and then we have these two like that. And in the 1,4 case, you notice that we have two planes of symmetry, this way and this way. So we have 1, 2. That's it. Everything else is the same. All right, so what we know is that the one that has 3 is the 1, 2. The one that has 2 is the 1, 4. And the one that has 1, 2, 3, 4 signals is the 1, 3. All right? Now, what about the proton NMR spectra? All right. Once again, we have the symmetry involved. So in this case, we have hydrogens here and here, which are the same, and hydrogens here and here, which are the same. In the 1, 3 case, we have a hydrogen between the two. We have a hydrogen across. Those are different. And then we have two hydrogens flanking those, and those are the same. And then in the 1, 4, if you think about it, all 4 of these are identical. So we just have one signal. They're all the same. Well, the 1, 4 is particularly obvious, right? Because we have a single signal only in the 3rd spectrum. So this is the 1, 4. And our C13 spectra that are connected there are the middle one on the left and the bottom one on the right. Now, what about the other two? Well, this is a little trickier. It has to do with chemical shift, and it has to do with this interesting difference that all of the signals are pretty much in one spot in the top spectrum, and yet they're very different in the bottom one. Remember that the aromatic benzene standard over here, and notice that that's a nice triplet, meaning that it's a proton next to 2 hydrogens. All right, let's look at these 1, 2, and 1, 3 a little bit more carefully. Remember that there is this effect that the hydrogens that are adjacent to a methoxy group are the ones that will appear over here in the 6 to 8 region. And that's also found for the ones that are opposite. So these are the positions where we find hydrogens that are shielded by the resonance effect of that donation of electrons by the oxygen into the ring. And so let's just see what we have in this case. For this top methoxy here, that would be these positions, only 2 of which have hydrogens. And for the bottom one, that would be these positions. But notice we've indicated all 4 hydrogens should be shielded. In contrast with the 1, 3, if we do the same thing, this methoxy on the left will take care of these hydrogens, and so will this other one. And there's a hydrogen out here which is not deshielded. And in fact, it's a hydrogen that should be a triplet because it's next to 2 identical hydrogens. And so our best bet is that this 1, 3 with this special hydrogen is this 2nd spectrum. And these 2 go together. And then that leaves the 1, 2 for this one. All 4 hydrogens being shielded by OCH3 groups. That's kind of tricky, kind of pushing it, but certainly the C13 you should be able to get. And if you could think your way through at least the 1, 4 in the proton spectrum, I think you should be able to do that. These 2, the distinguishing there, that takes a little bit more finesse, certainly beyond what your book talks about. All right, so remember, standard C13 NMR spectra are proton decoupled, meaning they don't show any coupling to their attached hydrogens. This makes it simpler to read a C13 spectrum than a proton spectrum, right? Because they're just sharp lines. There's no splitting. C13 is only 1.1% natural abundant. This has 2 consequences. First of all, we never see C13 splitting. The signals are all single sharp lines. And secondly, more scans are necessary, and there's generally more noise. Peak heights in C13 NMR spectra relate to how fast the nuclei relax. Now, I don't know how much that's discussed in your book, maybe not at all, but that is the reason why we see peaks of different heights in the C13 spectra. It's not because there's more carbon of one than the other. It's because it takes several seconds for the compound to get back to its equilibrium state, and we're continually pumping the system with RF energy in each pulse. And frankly, we decide to not wait the sometimes 30 seconds it takes for a C13 nucleus to relax. And what happens is some of them just don't relax and they don't give a good signal the next time and the next time, and pretty soon they're just not giving any signal at all. So we can't integrate a C13 spectrum. But knowing that carbons relax by trading their energy with protons that are attached to them, we know that a carbon with no hydrogens attached will be the one that's relaxing the slowest, and their signals are likely to be weak, with the carbon showing up as very small peaks. So this is really helpful in analysis, because if you see little tiny peaks in the C13 spectrum, you can be pretty sure that those are carbons that have no hydrogens attached. But also it makes it a little tricky because sometimes the noise is significant and those little peaks are just barely sticking out of the noise, or they might not even be sticking out of the noise because you haven't run scans. So they can be easy to miss. Solvent, CdCl3, for example, will show up in the C13 NMR because it has carbon in it. And that carbon, that solvent, has some C13. And in the particular case of CdCl3, what we see is a set of 3 equal height lines at 77 parts per million. You have to ignore them. And finally, we always start with an analysis of the symmetry of the proposed structure. Is there a mirror plane, an axis that would make part of the structure the same as another part? This is particularly important for analyzing C13 NMR spectra because the number of signals should match the number of sets of equivalent carbon atoms. And, by the way, because the lines are so sharp in carbon-13 spectrum, extremely rare that 2 lines will overlap exactly over each other. And we can almost always, if we blow it up, we'll see that 2 lines that are very close are actually 2 different lines. Okay, well, I hope that helped, and I hope you've got it.